Okay, fair warning, this is going to be an extremely nerdy video, so I wouldn't blame you if you wanted to skip this one, or maybe just skip to the end to see what the conclusion is. But basically today what I'm going to do is I'm going to show you what I did to build a heating demand model based on the historical weather data over the winter that's just gone. So I did this a couple of years ago, but back then I was using a different heating strategy with our air-to-air heat pump system. So this most recent winter, because I've used a different heating strategy, it requires a different heating model, which means I need to crunch all those numbers again. So what I'm going to do in this video is go through the process of doing that to show you what the sort of thing that you can do with this type of data and what it gets you in terms of how much heating you are expected to use over a particular winter, for example. So let me show you the spreadsheet. It's a bit complicated and it's not exactly pretty, but I'll walk you through it, and hopefully by the end you'll have a good idea of the sort of thing that I've been doing. So let's start with a nice attractive graph. This is the heating load for the house and the average temperature in degrees C, outside temperature, based on the historical data that I downloaded. I'll show you that in a second. But you see each of these blue bars represents 1 day's worth of heating and how many kilowatt hours of electrical energy we required to keep the house at a comfortable temperature for that particular day. And that's on the left hand axis here. So heating load in kilowatt hours each day, and on the right hand axis here we've got the average temperature for that day, and you can see so that's in the orange here. So you can see that the temperature when it was up at sort of 10 degrees ish, something in that ballpark, 10 to 15 degrees, the heating demand was reasonably low. But as soon as the temperature drops down towards sort of 5 degrees, 0 degrees, you can see that we get a big spike of heating demand, because obviously we need to keep the house warm. So this is not unusual. You normally expect when it gets colder outside you need a little bit of extra heating demand to keep the house warm. However, temperature is not the only factor that is important for how much heating you require. So let me just show you briefly, before I get any further into this, what data I actually downloaded and where I got that from. So if I scroll over to the left here, there's a whole load of numbers here, which I'll go through in a minute. But there's a link here to a source of data where you can basically put in your postcode and then grab historical data for whatever period you like. It's called Visual Crossing. You need to set up an account, but you can download data for free. What you have to do is download basically daily data, probably over a series of days, because you get a sort of limit of I think it's 1,000 entries per day that you can download. So if you want more than a few years of data, then you have to do it in multiple days. That's all I did. I just downloaded a few years at a time, and I've just got all of that in this tab down here called daily weather data. And you get an absolute ton of information. So obviously you get date. I've gone as far back as the start of 2010, and you get the maximum temperature, the minimum temperature, the average temperature. That's the one I'm going to be using. Feels like max temperature, feels like min temperature. All these other ones, those account for things like wind chill, things like that. Humidity, precipitation, everything else. And if I scroll a little bit further across, there's another interesting one that I discovered, solar energy. So this is effectively a measure of how sunny each given day was. Now, I believe that that's an important factor, and I will show you why I believe that in a second. There's also wind speed. I believe that's also an important factor. I mean, you can basically pick whichever of these metrics, whichever of these metrics you prefer to add into your model. So I picked a few that I thought were interesting, and I built a whole load of different models. So let me go back to the model tab here. And what I've done is I've built 6 different models. And when I say model, I mean using historical data to predict what the heating demand should be like on each of those given days, based on what the actual demand was over the most recent winter. So I kept a record of our heating demand on every given day, starting at the end of September. beginning of October and running all the way through to the end of March. So essentially the heating season for our particular house. We turned on the heating at the beginning of October, and we basically turned it off at the end of March. So I recorded that in this column here. That's why it's in purple, because that's data that I've recorded. So you can see on the 29th of September, we used 9.95 kilowatt hours of electrical energy to heat our house using our air-to-air heat pump system. And then I've pulled in some of the metrics that I think are important, and I've used those to then build what's called a multivariate regression model to then try and get a best fit for how much heating we would require based on these particular metrics over this whole heating period. And the way I've done that is I've done it up here in this little box with the different models here, and essentially it's done with an equation called line estimate, or linest. So if you see at the top here, I've got equals linest, and then there's a couple of ranges, and then true. I can't remember what the true means. Calculate B. Okay, so that just means that you're calculating an intercept, I think. And you can see here that it's highlighted these two columns for this particular model. Model 1, it's highlighted, I'm using the temperature, the average temperature on the day, and I'm using that to try and predict the heating load, which is the thing we're interested in. And you type that into this first column here, and it gives you two parameters. It gives you a slope, that's basically the best fit line between the temperature, the average temperature, and the heating load, and then an intercept on the y-axis, which is the heating load demand at 0 degrees C, basically. So what this model suggests is that at 0 degrees centigrade average outside temperature, we would require 29.6 kilowatt hours of electrical energy to keep the house warm. And for every degree C that the outside temperature decreases by, the amount of electrical energy we require increases by 2.1 kilowatt hours. Right, that's what that means. That's these two values here. And that's the most basic heating demand model that you can get. It just takes the average temperature on that day, and it basically just does, you put these two parameters into that equation, and you get the heating demand. And what you can then do is you can take that equation, and you can say for all of the data that I've gathered for the last winter, I can take that average temperature, I can put it through this equation, and I can get a predicted heating demand for that day. And that's what's in these boxes here. So model 1, you can see this is the equation. If I click up here, I take the average temperature, I multiply it by this parameter here, this slope parameter, and then I add on to that this intercept parameter here. And that's all that model does. And I just do that for all of the different days through the heating window. And what I can then do is I can compare the actual heating load against that prediction. And so that's these two values. And you can see that generally speaking, they're reasonably close to each other. So you know when this is this particular value here was 9.95, and the prediction was it should be about 10. And let's pick another one. Let's say a low one here. 1.51 kilowatt hours was actually used, and the model predicted 3.5. So there's a little bit of an error, but that's to be expected because there's all sorts of things that you can't necessarily account for using just the average temperature outside. So what I then do is I take the difference between those two values. So I take the difference between the actual heating load and the predicted heating load from that particular model, and I take the square of those differences. So I just I take the difference and I multiply it by itself to give the squared error. So this is the squared error between these two values in this cell here. And then in this box up here, this red cell, let me scroll across very slightly here. This cell here is the average. In fact, it's the square root of the average of all of these values here, right? So these are the different. These are the squared differences for each day between the actual heating load and the predicted heating load. I've averaged those, and then I've taken the square root of that. So this is what's called the root mean squared error, and this is a sort of measurement of how good a particular model is at predicting outcomes. And the idea is that you're trying to get this value as low as possible, because this value indicates a sort of typical error on each given day. And the value here is 4.376 kilowatt hours. So that means typically on each day, the model is roughly 4.376 kilowatt hours out. It's not that every single day. That's a sort of typical measure. Sometimes it'll be higher than that, sometimes it'll be lower than that. But roughly speaking, this gives you a measure of what's of roughly how good the predictions are from this particular model. And then what I did was I thought, well, okay, there are other factors we can include in a slightly more sophisticated model. So that's what I've done in models 2 through to 6 here. I've added extra information. So for model 2, I chose to use, as before, the average temperature on that given day. And I've also used the temperature on the previous day. So that's what I've called temperature of T-1. So that's the day before. So if I show you in this column here, you can see this is the average temperature, but this is the average temperature on the day before. So you can see that basically it just is the same value as the average temperature, but I've just moved it forwards one day, which means that this is yesterday's average temperature. Hopefully that makes sense. Basically because I believe that the temperature on the previous day is also important because of what's called thermal inertia. Basically your house acts as a sort of heat sink, and if the temperature today was cold but yesterday was quite mild, that means the outside of your house is effectively slowing down the loss of heat from your house a little bit, because it's a little bit warmer than you would normally expect based on today's current temperature. So in other words, if it was colder yesterday, then you would expect to use a little bit more heating because you're needing to replace the energy that would have been lost through the walls that previous day. Hopefully that makes sense. So that you can do the same thing. So I use this line estimate function here, but this time I'm using two parameters as the input to the model: the temperature and yesterday's temperature, to predict today's heating load. And you can do exactly the same thing as I did before. So I can take the prediction here, which is just the equation of this model. So this time I'm taking today's temperature multiplied by the slope of today for this model here of today's temperature, minus 1.43 kilowatt hours per degree C, and also take yesterday's temperature and multiply it by the parameter for yesterday's temperature. So in that case, minus 0.852 kilowatt hours per degree C for yesterday's temperature. And I can do exactly the same thing. So I've got the prediction and I've got the actual heating demand, and I can take the square difference, which I've done in this column here. Let me scroll across again. So once again, I'm taking the difference between the actual heating load and the model prediction, taking the square of that, and then in this cell here, I take the average of all of those values, all of these values here. Then I take the square root to give me the root mean squared error for that model. And you can see for this model, the typical error is now 3.98 kilowatt hours on any given day, which is somewhat less than the 4.37 kilowatt hours for the first model, which was based on just the today's temperature, average temperature. So what that means is that we've improved our model prediction by about 0.4 kilowatt hours per day, which means each day the prediction from the model is roughly 0.4 kilowatt hours better at predicting the actual heating load. So that's great. That means we've added extra information, and it does indeed mean that yesterday's temperature has an important impact on the model prediction. So that's great. That's useful to know. So that means what we could improve this even further potentially by, let's say, adding the day before temperature. And that's what I've done in model 3 here. I've got this temperature on 2 days prior to today, so the day before yesterday, and I've done exactly the same thing. So once again, you can see in this column here, this is the temperature on yesterday, the day before yesterday. So you can see here that if this was today's temperature, if this was today's temperature, this was yesterday's temperature, and this is the day before yesterday's temperature. And you can see that all I've done is just shift today's temperature by a day each time to give me yesterday's and the day before yesterday's temperature in these columns. And by taking, I can do again the line estimate, but this time taking those 3 inputs instead of just the first one or the first 2 to get the prediction for today's heating load, and that gives me then three parameters plus the intercept. But you can see that the parameters for the temperature, the average temperature for today, changes slightly, and now the temperature for the parameter for yesterday's temperature has changed a little bit, because we've now added this new parameter for the day before yesterday's temperature. Now, I found this interesting in comparison with Model 2. For Model 3, the impact of yesterday's temperature is somewhat less. It's now dropped to 0.4 kilowatt hours per degree C, but the impact of the day before yesterday's temperature is actually a little bit bigger, minus 0.48 kilowatt hours per degree C compared to minus 0.41 kilowatt hours per degree C for yesterday's temperature. Now, I found that interesting. I'm not entirely sure why that would be the case. It could be coincidence, just the way it worked with the particular weather data that happened over the winter. Not sure there's a reasonable physical explanation for that. What it suggests to me is that the temperature 2 days ago has more of an impact on your heating demand than the temperature yesterday, which seems a bit counterintuitive to me. So not entirely sure what's going on there, but it's interesting nonetheless. So let's do the same thing by taking the difference between the prediction, which again uses all four of the parameters for Model 3, and comparing the difference between that and the actual heating demand, and that's in this cell here. And you can see when I take the square of the differences and then take the average of those and square root them, I get a typical error, a root mean squared error of 3.76 kilowatt hours per day, which is a little bit better, again, compared to Model 2. So we're heading in the right direction. So I'm not going to labour the point too much, but suffice it to say that for Model 4, I included all of those same parameters again, temperature on yesterday, temperature on the day before yesterday, but I also included that solar energy metric that I mentioned earlier. So what that means is when it's sunnier, I expect there to be less demand for heating because we've got very big windows, and when the sun's shining through the windows, it tends to warm up the house a little bit. You may have noticed this. This is why conservatories get warm, for example. This is called solar gain in other terminology. So I added that metric in here, as you can see in this column. And for Model 4, you can see what I've done is I've done that same. Sorry, let me click there. I've done that same line estimate using those three temperature parameters and including the solar energy metric. And let's scroll back across to the model predictions, and you can see that including the solar gain parameter, the root mean squared error drops even further to 3.36 kilowatt hours. Compared to 3.76 kilowatt hours if you don't include the solar gain. So that is definitely important as a factor. And you can see here, because the parameter for that solar energy is negative, that means that the sunnier it is, in other words, the higher the solar energy metric, the lower the heating demand, as I would expect. So that's great. And you can see it's actually quite a powerful effect. It's not directly comparable to these exact values here because the value for the temperature is sort of kilowatt hours per degree C, whereas the metric for solar energy is, I think it's like joules per meter squared or something. So although the parameter looks bigger than the temperature ones, it might not have as big an impact as changes to the temperature as you'd expect. Temperature is the primary driver of demand. Yeah, you can see here that the values are roughly about the same, actually, a little bit less maybe. So anyway, so yeah, it looks to me that solar energy is a very important factor. So I'm going to count that as a win. And for Model 5, what I've done is I've added the average wind speed for the day, and I believe that's in meters per second. Let me go and check. Let's see what that says. Wind speed. Actually, it doesn't tell me what the values are. It just gives me a number. Maybe it's in knots. It's probably in knots, something like that. So okay, let's go back to here. So yeah, if we include the wind speed, then let's skip over all of the details and cut right to the chase. Including wind speed reduces the root mean squared error even further, down to 3.04 kilowatt hours per day roughly as a typical error. So if you compare that against the original model that just included temperature, we've gone from 4.376 kilowatt hours as a typical error down to 3.044 kilowatt hours. So we've effectively improved our model by, what's that, roughly 1.3 kilowatt hours per day, which that's pretty impressive, I would say. So the reason I think wind speed is important, and it clearly is because it's improved our model predictions, I noticed when it was windy over the winter that we definitely needed a little bit more heating, because I think what's happening is when there's a pressure, when the wind is pushing on your house, it's forcing air through all the little cracks in your house. You can't completely seal up your house, so there's always little cracks. So when there's wind that's pushing on your house from one direction or another, it's pushing the inside air that's warm out through all the little cracks, which means you need to replace the cold air that's come in. You need to heat that back up again, which means you need a little bit more heating demand. So when it's windier, you need a little bit more heating demand. This is not unexpected, I don't think. I think that's a reasonable assumption, and it does indeed appear to be the case. So if we look at the parameter for wind speed, this suggests that when it's windier, in other words, when wind speed increases, the fact that this value here, this parameter is positive, means that when it's windier, you need more heating. So yeah, that's as expected. And as before, we've got negative for the solar energy, negative for all of these three temperature ones. That's everything that you would expect, as we've mentioned in the previous models. So finally, for model 6, I thought, well, okay, what's the other thing that might be important? Well, potentially the average humidity during the day might be an interesting factor to include, because you could imagine that when it's more humid outside, that typically means that it's more humid inside. That's not always the case, but often it is. So when the air is humid, it requires a little bit more heating than when the air is dry. So you could imagine that when the weather is humid outside, you might need a little bit more heating. So I included that as a parameter, and in fact, it doesn't seem to make much difference at all to the results. So model 6, the result is very, very similar to the result for model 5. So in fact, the typical root mean squared error is 3.046 for model 6 and 3.044 for model 5. I'm going to say that those are basically more or less identical, which means that including humidity, surprisingly, makes no difference at all to my particular model using the data that I've gathered. I find that a little bit surprising. I imagined that there would be a small impact, but no, it seems not. So the best model actually of all of these is model 5, which is the one that includes the three temperatures, so today, yesterday, and the day before, the solar energy and the wind speed. So that's the model I'm going to use in the next section. So at this point, you may be asking yourself, well, what's the point of doing all that work? What does it get you? Well, for my purposes, what I wanted was a measurement of a typical winter. So what I've done is I've gone back through the historical data all the way back to the start of 2010, and I've gathered the weather data for all of that, for all of those days, all the way back to the beginning of 2010, and I've used the model parameters to predict what our heating demand would have been on that day, even though we didn't actually have our heating system back then. Obviously, this house wasn't even built then. But what it can do is it can tell you, given that weather data, the values on those historical days, what would the model have predicted our heating demand would have been. And that's what I've done here. So I've taken all of the model parameters from model 5, and I've also done model 6, but for the purposes of this, I'm going to just concentrate on model 5 because that was the best model. And I've taken all of the parameters and I've multiplied by the relevant historical metric for temperature and solar energy and wind speed and such. And that gives me a prediction for the heating demand on each given day in kilowatt hours, electrical input energy. And what I can then do is I can group that into each given month on each of those years. And that's what happens in this set of cells here. So I've got months, and so July, August, September, October, November, blah, 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 blah. And I've got each individual year running along here, running back from 2010 all the way through to the current 2025 season. And I've averaged up I've totaled the heating demand in each of those months for each of those years. And what that then gives me is a way of calculating a distribution of heating demand. So I can calculate the average. So if I let's just show you November, for example. That's the average of all of the Novembers between 2010 and 2024. All of these values here, basically. So it takes the average of these values, and that tells me what a typical November heating demand would be. And then, of course, I can also find the standard deviation, so the typical variation from 1 year to the next. What would it vary by on any given November might be plus or minus roughly this amount around about the average. So you could imagine, for example, that some mild Novembers would be somewhat less than this 442 kilowatt hours. Some might be somewhat more if it's quite cold for that particular November. So this standard deviation just gives you a measurement of how much the heating demand should vary roughly from 1 year to the next for a given month. So taking these average values for each particular month, I prepared a little chart down here. In fact, what I've done is I've compared it to the previous model that I made a few years ago. So the previous model I did using data from the 2022 to 2023 winter, and that's these values here. And I'm comparing it against the model that I have just shown you, the new model. So the previous model, I didn't include things like wind speed or the temperature on the day before yesterday. I only included yesterday's temperature and solar energy. So the current model is a little bit more sophisticated. It's got more parameters, should be slightly more accurate. And you can see in the chart here, this is comparing those two models. Now, what you can see, generally speaking, from this is that the current model, the new model, tends to predict somewhat higher heating demand for each given month compared to the previous model. This is not a surprise to me. This is entirely what I expected. And in fact, if you compare the two models, the sort of typical annual heating demand for the new model is about 19% higher than the previous model, so roughly 20% higher. And that's because what we're doing is this most recent winter, we were preheating the house overnight using cheap overnight electricity to pre-warm the house, which means that we need less energy during the day, and which means our home storage battery lasts a bit longer into the evening, which means we need less peak rate energy to keep the house warm. So despite the fact that we are genuinely using more energy to keep the house warm, we are doing so at a much lower cost. I've got other videos that explain that. Go and check out my stats videos that I do each month if you want more details on that, and particularly the ones over the winter. But given that it's costing us less, I think that's a beneficial strategy for us to be doing that. And not only is it costing us less, it's also keeping the house much more comfortable because the house is already warm when we get up in the morning. So yeah, we've never been more comfortable than we have over the last winter. So yeah, I would recommend that strategy if you're on a tariff like Octopus Go, for example. Running your heat pump overnight for a few hours during that cheap period can be quite beneficial. And this is the result of all that work. Basically, we've got this nice little chart here with the blue shaded area representing the output of that model. The expected on each given month is the central line there. And then these sort of fainter lines above and below are the plus and minus 1 standard deviation, which gives me an indication of whether or not the month was unusual in terms of heating demand. So you can see that generally speaking, so September, October, November, December were all roughly where we would expect, a little bit lower than a typical year, but well within the plus and minus 1 standard deviation. You can see that January was unusually cold, which means that it was above the plus 1 standard deviation line there. February was bang on. March was particularly mild, and you can see that it was below the minus 1 standard deviation line there. April, we actually didn't use the heating at all. It was very mild and quite sunny, so in fact that meant that we needed no heating whatsoever, so that made it very, very low in comparison to what the model predicted. The model predicted that we should have somewhere in the region of nearly 200 kilowatt hours for April, but in fact we used 0. And obviously we've not used the heating at all in May or June either. So there you go. That's the ultimate aim of all this modelling that I'll be doing, just so that I can get a nice chart like this. If you made it this far, well done. I'm very impressed, and I appreciate you sticking with me through all of that. But that's it for today. I hope you enjoyed that, and I'll catch you in the next one. Bye for now.